Hi everybody. So today we will be starting with the fourth topic in this lecture series, and today we will be focusing on this idea of multidimensional mapping of the data space. For a CUDA program, and also the related concept of synchronization among parallel CUDA threads. So just to get back into the overall perspective. So we have discussed this idea of basic computer architectures, and then we have migrated to some more detailed ideas on GPU architectures. We have introduced the basic syntax of CUDA programming. From this point, we are trying to get into some more finer details of CUDA programming, like how to handle complex data structures, how to synchronize threads which are operating in parallel and all that. So that's what we will focus on here. So if you remember our lectures on basic CUDA programs and examples of matrix multiplication and similar kind of programs that we discussed about, there was this notion of kernels getting launched, and as the launch parameters we are supplying certain parameters, which is the number of blocks and number of number of threads inside the block. So that's how we define them, and we also said that this is something we will take up as a future topic. So this is where we will discuss it finally. So when we say that a CUDA kernel is getting launched, essentially I launch a set of threads. Now these threads are packed into a finer element which is known as block. So essentially I say that I will launch multiple blocks of threads, and this entire arrangement of threads is called a grid. So in general, when I am talking about the overall idea of CUDA threads that are getting launched, I am launching a grid of threads. This arrangement of the grid is it can be defined like this, that I can say that essentially a grid is nothing but a 3D array of blocks. So inside a grid, I have entities known as thread blocks or blocks, and I can pack the blocks in 3 dimensions. We will see such examples, and then again the similar concept will repeat inside blocks. So I can say that a block is nothing but a 3D array of threads. So overall I have the threads arranged as 3D arrays, in 3 dimensions in packings of data structures called blocks, and the blocks can again be arranged in 3 dimensions into packings which are finally defined as grids. And this idea of 3-dimensional definitions is corresponded to by a specific data structure type, which is a specific structure which we define in CUDA in the extension of in the CUDA semantics, and we call it as a structure called dim3. So if I am not really interested in extending in the dimensions, the unused dimensions are set to 1. Let's see some example. So suppose I am trying to define such a 3-dimensional packing of the grid of threads. So this is how I will like to go about it. So when you launch a kernel, so this is a launch example of our vcat kernel, the vector addition kernel. So if you remember, we are supplying these 2 parameters. These parameters were corresponding to the number of blocks in your grid and the number of threads per block. Since these are individually all 3D packings, so both of these x and y correspond to a dim3 data type. That's the structure that we have discussed earlier, that we use this structure type dim3. So you define it like this, that x is a packing of blocks where you have this many number of blocks in the x dimension, and you don't proceed in the y and z dimension. So these are set as ones. Fine. So essentially you are saying that, okay, you are given some n, the total number of elements to add for and then you divide it into blocks of size 256. So overall you will have ceiling of n by 256.0, ceiling of n by 256.0. I hope you can see this. And so you are essentially trying to define this many number of blocks, and this 256 is here because essentially you are defining a block as a collection of 256 threads. Again, you are not going to multiple dimensions while you are defining blocks. So the blocks are also defined by this type y, the variable y, whose type is again dim3, and this y is again also defined in the single x dimension, that it is going to contain 256 threads. So, overall you have n number of threads, it is divided into n by 256 number of blocks. Inside each block you are going to have 256 threads. This is the arrangement that I am choosing here, right. So, with this definition of x and y, when you are launching the vcat kernel, what is happening is you are passing this x and y as launch parameters for the kernel. So, when the kernel is launched, the threads get packed into, I would say, tightly knit blocks of 256 size, and in total this n by 256 number of blocks are getting launched. I can write this formally like this, because this is the usual way you will define it. Every CUDA kernel will expect as launch parameters 2 elements here. Each of these elements are dim3 tuples. However, since this is a simplistic single dimensional kernel, I can also directly write like this. So, this comma actually separates the number of blocks and the number of threads per block definitions. So, since I have only 2 entries, the CUDA compiler would be smart enough to identify, okay, well, then I am really talking about a single dimensional grid containing blocks only in the x dimension, indexed in the x dimension, and again inside the block also I do not have multiple dimensions really. It will automatically assume this kind of definitions as discussed earlier here, and so it will also think that inside each block I have got all the threads packed in x dimension. Fine. Now, this is the most important part. I believe in the earlier program example, simple program, we have already discussed that you have a simple CUDA program. There are certain variables like thread IDs and block IDs which get automatically defined, and every thread has got its own local value of the thread ID and block ID. We will get back to that again from the point of view of a multidimensional grid and block here. So, in general, when we are defining a 3-dimensional grid containing the block indices in 3 dimensions, essentially the system, the runtime system of CUDA would automatically define these variables. So, these are essentially system variables that the program can always access. You do not need to define them, or you cannot actually define or initialize them. So, the moment you launch the kernel with suitable launch parameters, you have automatically available values of these variables, that okay, for this CUDA kernel what is the grid dimension in the x axis, y axis and z axis. These values can range from 1 to 2 raised to the power 16. Okay. So, that is the maximum dimension of the grid allowed in each of the 3 axes. Okay. So, for each block we will have these 3 block ID variables providing me that block's actual ID in the 3D's collection of 3D packing of blocks. That would mean for every individual CUDA thread I would have a collection of these 3 variables. That means I will have their values available, that the thread can transparently see those values of what is the block ID, what is the block ID in the x dimension, y dimension and the z dimension. And of course, for all the threads sitting inside one block, these values should be same. That means for all the threads inside one block, they can all access this block ID x, block ID y and block ID z, and this combination of values should be exactly same, because they are all technically inside the same block. So, just to summarize, that all the threads in the same block would see the same value of these system variables block ID x.x, block ID x.y, block ID x.z, and again we can understand definitely that these block ID x variable values should be varying inside this range of grid dimension, right? Why? Because it is so obvious, because you are essentially defining a grid which is constituting a 3D packing of blocks. The grid is a 3D packing of blocks, and each dimension, the grid dimension is ranging from 1 starting to the power 16, right? So, every block ID is definitely in the x direction or the y direction or the z direction, whichever way you go, the block's ID has to be less than the grid's allowed dimension in that x, y or z axis, right. Now, there is some other significantly important thing here, which is that a block's dimension is limited by the total number of threads that you are allowed to pack inside a block, and this number is 1024. So, when you are launching a CUDA kernel, the block's dimension, the block's total number of threads packed inside the block cannot be more than 1024. Now, of course, this is a number that may vary with architectural families, with maybe in future with significantly higher compute capable architectures of the GPUs, this number may change. This is something which comes as a restriction based on the architectural content, the maximum register file size possible and all that. So, right now we can assume that a block has a max size, that means there is an upper bound on the total number of threads that you can pack inside a block, and it is 1024. So, that automatically restricts your possible block ID, your possible definitions of a block, right, because as you can see, we have given here as an example 4 possible block definitions. So, in the first definition, we are saying that okay, let us pack all the threads in the x dimension. So, you are defining a block of size 512, all the threads are in the x dimension. So, that is perfectly fine, because the total number of threads is less than 1024. Same thing for the next 2 definitions. However, if you look at the 4th definition, we are saying that okay, let us define a block where you have the threads 32 threads in the x dimension. You are letting the thread ID x.x variable go from 0 to 31, and similarly thread ID x.y 0 to 31 and thread ID x.z from 0 to 31. So, if we do that, then the total number, that is 32 cross 32 cross 32, the number of threads is of course greater than 104. So, this is not allowed. So, as further example of grid and block declarations, let us consider this following piece of host code. Now, why again do I bring in this idea of another host code? Because of course, we had another example here. Well, this was a much simpler example, because technically we had the packing of blocks all in the one dimension, and inside the block the packing of threads also in the one dimension. Hence, just to visit a more complex example, let us look at this. So, here we are saying that okay, let us consider a grid definition where the blocks are packed in 2 dimensions. So, in x dimension you have 2 blocks, and in one dimension you have 2 blocks, and also you have inside the block you have a 3D arrangement of these threads. So, you have another DIM3 type Y with this arrangement 422, and overall you are making a vcat kernel call with launch parameters x and y. So, this would create a memory layout in the device, and the kernel, when it is launched, the corresponding memory layout for that we have a picture here. Now, this is something which is very important. We are just trying to understand through this picture that what is the impact of this kind of definition of the packing of threads on the variation of the thread ID and block ID indices, like that. So, since I have defined the grid here as a 2D arrangement, so we have, as you can see, this block ID z variable always 0, right. So, that is why in the this is like more of a hierarchical figure. So, on the top I just show the arrangement of blocks, right. As you can see, we have defined the number, the blocks collection as 2 to 1 x. So, the first entry is corresponding to the x dimension, the second entry corresponds to the y dimension, and the third entry corresponds to the z dimension. So, coming here, the way the indexes are arranged here is just the opposite. So, at the very first MSB, I would say the most significant position, the LSB, the least significant, at the extreme right, I have the x dimensions encoding, which is increasing, and then I have the y dimensions encoding, and then I have the z dimensions encoding. since z is set as 1 here, that means we are never going to increase the z index, so it's always 0. Of course, the index calculations start from 0 and they go up to the max dimension in the x or y space -1, right, which would mean here for this definition my thread indexes in the x dimension are going to vary between 0 to 1, y dimension 0 to 1, and z dimension has to be fixed at 0, right. So that's what we have here. All the z dimension encodings are set to 0, right. The x dimension encoding, they vary between 0 and 1, as you can see 0, 1, again 0, again 1, and as we can see that the y dimension encoding is also varying from 0 and 1, but if we are trying to show the arrangement here, we are increasing in x first and then we are saying that let us increase in y, and we are saying that okay, the blocks are arranged like this one after another, right. But now we need to look deeper, right. So this is how we will have the blockDim.x variables varying for each of the blocks. So we are having 4 blocks and these are the 4 possible triples or collections of blockID variables that we will have for each of these 4 blocks. Now what about the situation inside the block? Of course, inside the block I am going to have the threads and I am going to have 4 times 2 times 2, that is 16 threads, right. How are the threads going to be indexed, right? So as we can see that this is again a packing in the 3D space, and you are going to have the threadIDX.x variable to range from 0 to 3, threadIDX.y to range from 0 to 1, and threadIDX.z again going to range from 0 to 1, right, and that's how we have it here, right. So we start with the thread with indexes all 0, and then I have the threadIDX.x increasing to 1, 2, 3. Again we will start from 0. The threadIDX.y increases from 0 to 1, right. So I have again 4 consecutive locations where it's same the encoding at the x position as the first 4, but in the y position we instead of having a 0 here we are having a 1 here, right. And then again this thing continues. This similar pattern would continue. It's just like counting over multiple dimensions. Instead of now having 0 in the z dimension, you just start having 1 in the z dimension and repeat the scheme again. So then considering one block, inside that block all the threads would be having index triplets arranged like this. If we specifically pick up one single thread, for example, let us pick up this thread. So this is a thread for which, as I can see, that the system variables would be assuming values like this. So the threadIDX.x variable would assume the value 3, threadIDX.y variable would assume the value 1, threadIDX.z variable would assume the value 0. For this thread, the blockID variables would all assume values from here. Similarly, I would have this arrangement repeating for the next block, again this arrangement repeating for the next block. So if I pick up some thread from this block, it would have a specific collection of threadIDX, y and z, right, and for that the blockID variables would have these 3 values, right. I hope this is clear that how each thread can figure out, can see what is the corresponding system variable values for it. That means if you are going to write a CUDA program, you can actually compute that what is the actual position of a single thread among the sea of threads by computing a suitable expression made using these variables of threadIDX, y and z and blockIDX.x, y and .z, right. Because for every thread, this collection of all these 6 parameters is going to be unique. It may happen that I have this triplet of threadIDX.x, y and .z same for 2 different threads in the entire kernel, but of course they have to be from different blocks. So, although the thread IDX collections are same, the block IDX collections have to be different. So, in that way I can say that for every thread, this collection of the overall 6 parameters will always be unique. Now, let us take an example here that so how really is this definition of threads and blocks going to help me? Suppose I am trying to use this packing of threads to define a 2D matrix. So, I have an 8 cross 8 matrix, right, and I use that packing of threads to define the matrix. How does that work? Well, as we can see that I am actually having blocks of size 16 here, and overall I have 4 blocks. So, the total number of threads that can be packed inside this grid of blocks is 4 times 16, which is 64. And here I am trying to define a 2D matrix which is in total going to have 8 cross 8, that is 64 elements. So, I can use this arrangement of threads for storing all the values of the matrix or maybe computing the values of the matrix. So, let us see that how these indexes can be derived for each thread. So, first of all, for representation purpose, we just color code these blocks in different colors, these 4 blocks in different colors, and we just focus on the green block here and see that okay, for one of the specific threads here, the thread IDX parameters are 0, 1, 3, right, and the block IDX parameters are 0, 0, 1. Now, just to understand that inside this entire collection of the locations of the 2D matrix, how can this thread figure out exactly what location does it correspond to? So, for that we can see that how these different parameters or the system variables get linked up, and how those parameters can be used to compute a position of this thread with respect to the overall collection of all threads. Now, for doing that, we can observe that these are a few relations that are always going to be true. So, what is that? So, what is the current block number for a given thread? So, I can find that out by evaluating this kind of an expression, right, that the okay, for this thread the block number is given by the block ID in z dimension multiplied by the dimension of the grid in x and y dimension, because okay, when I am talking about the block ID in z dimension, that means let the value be 2, that means I have already come across a collection of this many, that is grid dimension x times grid dimension y number of blocks in for 2 values of block ID x dot z, right. After that, you will have to cover whatever is there in the y dimension. So, that is why you will do a block ID x dot y times grid dimension dot x, and finally, after that you have to enumerate okay, what is the remaining number of block ID x dot x, and that would give you the exact number of the block. So, I hope this is clear, like we are trying to figure out that okay, given these parameters, how do I find out in which block I am right now positioned? How can each thread find out its corresponding block number out of these blocks? So, in this representative example, as you can see, you have 4 blocks. For this specific thread which is in block 1, how can it figure out its block number, that the block number is indeed 1? How can it do that? So, you can just apply this system of equations and try to evaluate. So, what do you really get here? So, you are going to get that okay, the block dimension in the z axis is 0. So, this part does not work. Then the block dimension in the y axis is also 0. So, this part of the expression also does not come into play. So, you are only concerned about block ID x.x, and that gives you 1. Similarly, for example, suppose I am talking about block 3 and we are talking about one thread in block 3, and how does it figure out that okay, it is indeed in block 3. So, for this thread the block ID x dot z is 0. So, this part of the expression cancels out, right. Block ID x dot y is 1. So, that would get multiplied by the dimension of the grid in the x axis, which is 2, right. Now, why is that? Let us just review back. So, as you can see, the dimension of the grid in the x axis is 2 and on the y axis is also 2, right. So, based on this, since this is 1, so and this is 0, so this part is completely cancelling out, and the next part, for that I get the block ID as 1 gets multiplied by the grid dimension which is 2 plus the block ID x dot x, that is 1. So, overall you have 2 into 1 plus 1, that is 3. So, just to work it out here. So, we will just see that if I am speaking of this block, this value comes as 1 times the grid dimension 2 plus this, so that would be 3, right. So, just to explain this expression again, for example, in here we do not have really a case for the first part. How would that have come? Suppose I have got the grid in an actual 3D space, right. So, then you would really be counting first collection of blocks in the z dimension. So, you will have some number of blocks in the z dimension, and in that way, so suppose in the z dimension you are sitting at position 2, that would mean you have already come across this kind of 0, 1 and 2 layers of blocks, right. So, your block ID of in the z dimension would get multiplied by these many blocks, right, because this is the packing in the x direction and the y direction. So, that is how this block ID x z will get multiplied by the grid dimension in x and y axis, and then you come to your current dimension position in the z axis, and then you count the number of blocks that are there in the y dimension, you multiply it by x. So, that would exhaust your count by all the blocks located in the x dimension for each block ID y value, and then finally you would add the block ID x. So, we will see that it would of course get better in terms of examples once we see some example code here. Now, in that way we can compute the number of the block for a given thread. How do I really compute the exact number of the thread or the global ID of the thread with respect to this entire arrangement? So, the thread number would be given by the z index of the thread multiplied by the dimension of the block in the x and y axis, because actually when I am talking about the z index of the thread, then I have exhausted the previous blocks, this many blocks, this block dimension x times block dimension y number of blocks, right, but times this thread ID z, and then you have to compute this term which is thread ID x y times the block dimension x, and then you have to just add the dimension value in the x direction. Let us take an example to make things much more clear here. So, for example, if we consider this thread, so the thread ID x dot z value is 1, and so basically this is your thread ID x dot z, and then your thread id x dot y value is again 1, and your thread id x dot z value is again 1, sorry, this is 0, and the block dimension in the x axis, as you can see, for here is 2, block dimension in the y axis is also 2, right, and this value is also 2. So overall what you get is 1 times 2 times 2 plus so that's 6. Now if you look at the position here, so we are considering this 1 1 and 0. So this 1 gets multiplied with the block dimension. I believe the block dimension, let me just check back once. Sorry, okay, so in the x dimension it's 4, and then y is 2 and z is 2. Sorry, so here we just replace this entity by a 4, and also just check, this is also a 4. So in x dimension it's 4, y dimension is 2. So now these are fine, and this is the thread idx in the z direction, in the thread idx in the y direction, and here again the block dimension is 4. So that gives you 8 plus 4, that's 12, and as you can see here the thread id is indeed 12, right. Sorry for this delay here. So overall we can see that if you are given the proper thread indices, then the system variable values get automatically initialized, and each thread can compute its block dimension and the thread dimension figures, and then it can figure out what are the block id and thread id values. It can compute which block it is in, and inside the block which thread it is in. For example, if I pick up this threads corresponding block dimensions, since they are 0 0 and 1, it will easily apply this formula. Only the last term would be useful, and it can figure out that the block number is 1. I think for block number we didn't have a big example here because the block dimensions are really small in value, but just map this idea of thread number computation here, and you can easily see how the block number can be computed for a more complex example here, right. So and the next important thing would be that okay, a thread number can be computed for a position of the thread inside this block, and a thread can also find out what is the number of the block in which it is positioned. Using these two values, the thread can find its exact position in the global thread id variable, that is its exact position among all the threads that have been launched, which is nothing but the global thread id is equal to the number of blocks that have been covered up to block 1. So in each block you have got how many threads, block dimension x times y times z, these many threads, plus the thread's position in the current block. This gives the thread's global id, which we call as the global thread id. So this is the exact position of the thread, or the exact index value of the thread among all the threads that have been launched by the kernel. Well, I think with this we should be ending the lecture here. And thank you. We will explain more on this in the next lecture. Thanks.